But anyway, so the bottom line is, what I recommend is that this kind of 135 azimuthal angle from the sun and looking out at around 30 or 40, it minimizes the sun glitter. You miss the shading by the ship or the instrument, and it has minimal variability in the row values, so you're more likely to get a reasonable value. But this does need to be updated for wavelength dependence, and I just, once again, haven't gotten around to doing that. So it's another project for retirement. Okay, and as I mentioned, Zhongping Li has put out a paper here in 2010 where he talks about row dependence, and it can be significant, and sometimes it really doesn't matter. Okay, you've done this technique, which avoids the whole row business. So here you have the Carter method. You've got this surface glint you have to get rid of with the magic row factor. Zhongping Li puts his little collar on here. It blocks the sky radiance, so you really are detecting only the water leaving radiance. Great idea for working on the dock. Not so practical if you're on the ship and you're, 4 meters above the water hanging over the edge of the ship and the waves are 2 meters high. It's a little hard to keep the collar. You have to have a collar that's 4 meters long, and that's just not going to work. But for this kind of work, definitely the way to go as far as I can tell. The other way to get water leaving radiance is from measurements below the surface. And then you have to some way extrapolate those upward. So there's several techniques people have used. One of them is you measure LU at one or more depths. So they could be fixed depths on a mooring, or they could be a profiler. And then you extrapolate the LU in the water from wherever you started measuring up to the surface, and then you get that LU from just below the surface to just above the surface. Then you have an LW and divide by ED in air. The problem, of course, is you have to extrapolate through some distance of water unless it's absolutely dead calm and you can really put an instrument 2 centimeters below the level water surface. But in the real world, like on the Mobley buoy, the measurements start a few meters down. And so you have to do that extrapolation. And even in very clear water, depending on which wavelength it is, that loss of light and going from LU from here up to here is significant. So you really have to figure out how to do that extrapolation. And the other thing people do, and of course that means you have to come up with a KLU. Well, how did you get that? Oh, you fit your data to these 3 points, and you hope for the best. The other thing is people will measure LU and ED in the water, and then they'll look at the ratio of LU over ED in the water and extrapolate that upward and through the surface, and then that gives you RRS, because this LU over ED in the water is basically RRS. It's ratio of upwelling radiance to downwelling irradiance. So you, rather than extrapolate the LU, you extrapolate the ratio upward. And then, of course, in the water, you now have instrument self-shading problems, so you have to correct for those. And those, of course, depend on IOPs, mostly the absorption coefficient. They depend on sun zenith angle and the size and the shape of the instrument. So I have this thing called the law of conservation of misery. And, there's no getting around it. You either have to come up with the magic row factor, or you have to go over here and come up with the magic KLU factor, one way or the other, to do the extrapolation. So there's no easy way to do it.
Does anybody do it that second way? I've never
Well, let me skip ahead here. There's a big paper by Hooker in 2000 where they compared several different ways of removing surface glint and several ways to extrapolate upward from in-water measurements. And so they did moorings in water. They measured LU and ED at fixed depths. They extrapolate the ratio upward. They had surface floats like we had out here, so they measured LU in the water, extrapolated that upward, divided by ED in the air, and then they did profiles of LU and ED and extrapolated. Oh, I said that already here. Oh no, sorry, this is a mooring and this is profiles. So they did everything they could think of and then compared them all. And so there's about like 3 of each, and then they concluded that one of the in-water ones was the best, but I don't remember which one it was. So anyway, you could look at that paper. So if we back up here, I mentioned instrument self-shading. Okay, so here's a paper from Gordon and Ding long ago where they modeled instruments as being little cans with some radius, and then they did simulations of sun coming in. Here's going to be the shadow of the instrument in the water. The instrument is looking down to measure LU, so it's always looking through some bit of its own shadow before you get out into the real sunlit ocean, which is what you're interested in. So he did this big Monte Carlo study, and it's a function of all these different parameters, the depth, the sun angle, the solid angle of the instrument, and so forth. And what it all boils down to is the error you get from self-shading really depends on the product of the absorption coefficient and the radius of the instrument. And Ken mentioned this the other day. So here, for example, here's absorption times instrument radius, and this is 0.01, 0.1, 110. So let's say you have an instrument that's just 10 centimeters in diameter, but the water has an absorption coefficient of 1 per meter. So you'd have 0.1 for the radius, 1 for the absorption. That's this value here, and you look up and you say, I'm making about a 30% error. Now, if it was clear water, so the absorption was only 0.1, then you'd have radius 0.1 times absorption 0.1, that's 0.01. Well, that's still like 5% error, but maybe you can live with that. But if you have this big instrument, it's like 50 centimeters in diameter, or you've got this big instrument package, let's say it's a big cage here, and it's a meter square or a meter in diameter, and you've got your instrument there, well, now you're seeing the shadow of this whole cage. So now R is 1, and absorption is, let's say, 1. Now you're out here, oh, well, it's just an enormous error. It's like, close to a factor of 2. So anyway, the moral of the story here is you want to make your instrument as small as possible. So there's, going from the old instruments that were this big down to little instruments today to make this R as small as possible so that for a given water body, you're coming down here on the curve. But anyway, the instrument self-shading is significant in anything except the rare wavelength where it's really, or rare water body and the wavelength where it's really clear and you have a really small instrument, then maybe you're only off by 5 or 10%. But usually you're up in the 25 or 50% error range just due to instrument self-shading. So it's a big deal. Okay, so I think I've already said that, this upward extrapolation business after you correct for self-shading requires estimating KLU, and we saw from one of the plots today that sometimes KLUs looks a little hard to get the right value. Yeah.
For self-shading instrument, most of the time you measure 80, right? So you can.
Well, you're measuring LU here is what we're talking about.
Right. And if you have both, like on the C-ups, you could derive 8. Is that what I understand? And then.
No. So the instrument self-shading is for the LU measurement.
What do you need on this instrument if you measure AOPs to get the 8 to correct for its self-shading?
Well, that's the catch, of course. If you knew the absorption coefficient, you probably wouldn't be doing the remote sensing to begin with. But all Gordon's showing is that this is not for retrieving absorption. It's to show how the error depends on absorption coefficient and size of the instrument. So then if you want to do the correction and you know your instrument, then you do need to know the absorption coefficient in order to do that correction. And of course, in the red wavelengths, you kind of could use water, but back in the blue, you now have to make some guess about, oh, well, the chlorophyll was this, and therefore the absorption at 440 was that. Ken?
I think you're right. If you had a LU, you could combine the two and do at least an approximate inversion to get A, and then try to correct your.
Yeah.
So it would do something like that.
Yeah.
Yeah.
Okay, and I think we've already said all of that. So these in-water methods can have just as much uncertainty as the above water. That's the bottom line. And I've already mentioned there is this paper that's in your library where you can look at all the different ways they did things, compared them, and here's a plot. This is LWs as retrieved by all the above water measurements versus the best in-water measurement, which they called method S84, and I don't remember which one that was, but in principle they should give the same answer, and with a lot of effort, yeah, you get pretty good results here. There's dots in here for clear sky, case 2 water, clear sky, case 1 water, and case 2 water with an overcast sky as these points down here. The open points kind of underneath are the clear sky case 1, and the black points are the clear sky case 2. So you see, you can get pretty much the same LW regardless of which technique you use. It just takes a lot of effort to do that. And then just a couple more view graphs now to talk about what's this atmospheric correction problem all about. Well, here's top of the atmosphere radiances computed for wind speeds of 0, nadir viewing, and this is for a particular location basically off of Hawaii where Ken's Mobley would be, that area. So I'm looking at the nadir, I'm looking 30 degrees east, 30 degrees west. It's clear skies, it's hazier skies. There's a wind speed of 10 and 30 east, 30 west, clear and hazy skies. So you get a bunch of top of the atmosphere radiances. Those all depend on viewing direction, atmospheric conditions, that's wind speed on the surface. So you have all of these top of the atmosphere radiances, and every one of these had the same water leaving radiance. This is generated by a coupled hydrolite and Modtran model. Modtran is an atmospheric model like hydrolite. I couple those two together, and these were simulations done for a satellite that's proposed called Hysperi. Anyway, I did these simulations, and so the game is I'm going to give you any one of these curves and say, here's the top of the atmosphere radiance, give me the water leaving radiance. So that's what atmospheric correction is all about. All you know is, well, I know what direction I was looking, I know where the sun is, so that would eliminate some of these curves. But then the hard part is you don't know at the moment you get the image what the atmospheric properties are. Is it a really clear atmosphere? Is it hazy? Are there absorbing aerosols? Are they sea salt aerosols? You know, all of those things. So you're still going to end up with some of these curves here. They'll be significantly different, and then they all have to come down to a water leaving radiance. So that's the big problem. Here's another plot. Okay, so this is level 1B, top of the atmosphere data, radiance units. And just to look at what's here, so the purple curve is the irradiance over on this axis. So the solid line, there's the solar irradiance at the top of the atmosphere, and the dotted line is how much of that got through to the sea surface. So, and this is like 10 nanometer wide bandwidths, I think, so you don't see all the little Fraunhofer lines. Okay, you do see these big atmospheric absorption features, and of course, what makes it to the surface is less than the top of the atmosphere because some of that was absorbed and some was scattered back out to space. But that's what that looks like. If you look at LU here, the solid blue is the top of the atmosphere radiance, so that's what your satellite's going to measure. The dotted blue here would be the surface total irradiance if you were right at the sea surface looking downward. And of course, this is a whole lot less than this, because in getting from the sea surface to the top of the atmosphere, you've added in all this atmospheric scattering and so forth. So here the yellow curve is the atmospheric contribution to the top of the atmosphere part. The red curve is the sea surface reflectance, so both sky reflectance and glint. So that's a pretty big contribution. The surface part is bigger than the top of the atmosphere part, because in getting from the surface to the TOA, part of that was absorbed. And then down here, there's a dotted green line. That's the water leaving radiance at the surface. Here's how much the solid line of that made it to the top of the atmosphere. So the bottom line is you're going to be given the blue curve, and you need to retrieve the dashed green curve at the bottom. It ain't easy. So here's another plot of that same data where I look at what of the total at top of the atmosphere radiance, what fraction comes from the different contributions. So the green curve here, that's the water leaving radiance contribution to the total, and you can see it's sort of 5 to 10% in the blue and the green wavelengths. The surface reflectance part could be less than 10% here, could be 30% out at 800. The Rayleigh scattering part by the molecules in the atmosphere, at blue wavelengths, they're about 75% of the top of the atmosphere radiance. Out here, they drop down to say 20% and keep going down. That's the one thing that you can actually really accurately remove from the signal. The kind of gray curve here is the aerosol contribution. That's 15 in this particular simulation, 15% back at 350, but it's more like 60 or 70% out in the near IR. So if you take the total atmospheric part, which is Rayleigh plus aerosol, there it is, and you look back at the blue here, that's typically about 90% of the total, or at least 80%. A lot of simulations, this atmospheric part may be 95% of the total. So you have to some way remove all of that stuff and finally end up with that. Okay, the one final slide here is that the terrestrial people have it much easier than the ocean people, because the typical ocean, let's say, irradiance reflectance is 2, 3, 4%. On land, it's 30, 40, 50%. You know, even if you're in a dark green forest, you're still getting maybe 20% reflectance. If you're out in the desert where it's sandy, you're getting 30, 40% reflectance. So the atmospheric contribution is much less relatively much less than the surface reflectance for the terrestrial people. And for the ocean people, the atmospheric contribution is almost everything. The other thing is that the terrestrial people are usually concerned with just mapping what kind of surface it is. Oh, it's forest, it's desert, it's water, it's cropland, it's houses, it's roads, whatever. They're not doing something like retrieving water optical properties. They're only retrieving surface properties. So there's a whole body of techniques that they've developed where you have a library of measured reflectances for everything imaginable, from, you know, green grass to asphalt to, you know, building roofs to forests and deserts and wet ground and dry ground and all of this. And they look at their image, they may do a little atmospheric correction, and then they match the spectrum their imager sees with some spectrum in their database, and they say, oh yes, this pixel is a road and this pixel over here is a forest, and they're done. So life is really easy. In our case, you know, we're trying to retrieve something from the water, and our reflectance is maybe 1/10 of what their reflectance is, and we have to, you know, get rid of all this atmospheric effect and finally get to some kind of information about what's in the water. And it's enormously more difficult than the terrestrial people have to work with. And so there's a whole body of things like called supervised classification techniques, and thematic mapping means you're just mapping what kind of surface it is by themes like land versus forest versus highways, whatever. A huge body of techniques there, and they simply do not work for the oceans. That's why we don't use them. And the terrestrial people never understand that. They always say, well, why don't you use this technique that Joe developed in his paper last year? And the answer is, well, because all it's giving me is a classification of the surface. I need to know chlorophyll, bottom depth, CDOM absorption, whatever. And at that point, you've lost them.
Can I add something to there?
Yeah.
Sort of a funny story is that when Modus Terra was launched, the first EOS launch, the atmosphere and land and oceans teams were part of it. And they wanted, after launch, NASA, the managers were saying, okay, within a month, we want you to be putting out papers with using Modus. The land people, I think they had their papers written before it was even launched. They within a month, they had papers using Modus data. The oceans people, we've never figured out how to calibrate Terra well enough to use for ocean data. The vicarious calibration stuff I talked about the other day from why we use Mobley, they don't need calibration within a few percent or 5%, I think, to get what we want. So it is so much easier.
Yeah. And then a lot of this classification business, I mean, this is huge for the military. And all they want to do is have a sensor that looks down and says, oh, there's Osama bin Laden's house, drop the bomb there. That's the end of their problem. Well, you know, it's just a little harder for us. Okay, so I was wandering around Lhasa one time in Tibet, and, you know, I ran into this old gal. She was doing her circumnavigation things around the Jokang, which is like the Tibetan Buddhist equivalent of the Vatican. So I think she had about 3 teeth. She's probably 200 years old. She was about this tall and had this prayer wheel that was bigger than she was. So anyway, she was quite a character. She wanted me to take her picture, and so I often wonder, you know, like I wish I spoke Tibetan and I could ask her, like, well, what was it like to grow up in Tibet in 1920, long before, you know, Tibet was still a closed country, etc., and now you're in a world where there's tourists coming to Lhasa and taking your picture, and, you know, what do you think about all this? So anyway, then there's a lot of monasteries and stuff around Tibet, and this guy was painted on a rock that was about this big, and he looks like a pretty nasty guy. He's actually a protective deity for the Buddha. So if you want to go in and mess with the Buddha, you have to get past this guy first. And obviously he's, you know, pretty tough character. He's got all these flames coming out and big swords and all of this. So I'm not up on my Tibetan Buddhist deities, but there's a lot of these guys around. It's fabulous artwork. I have, you know, walls full of Tibetan tankas and stuff at home that I bought in places like here and Nepal and so forth. So it's fabulously beautiful, intricate, very colorful artwork. So that's another place after you get back from kayaking in Greenland, you know, definitely take a trip to Lhasa. And the highlight of Lhasa, of course, is going through the Potala, which was the Dalai Lama's, I don't know, palace or whatever you want to call it there. It's something like 1,100 rooms, and you go in one room and there's be like the casket of the 6th Dalai Lama, and it's made out of 12,000 kilograms of gold with 15,000 diamonds embedded in it. And you think, wow. And then you go to the next room and, oh, well, there's the tomb of the next Dalai Lama, and it's got twice as much gold and twice as many diamonds, and it's just mind-blowing place. So I always tell people, if all you did was fly to Lhasa, take the tour of the Potala, and fly home, it would be worth it. It's just an amazing place. Okay, that's it for now. It's 10:30, so what, take 20 minutes? Is that? Sound reasonable? Okay, so back at 10 till 11 then.